Hello, welcome to lecture 19. We're going to be talking about direct mapped caches. A couple of deadlines coming up next week. Please pay attention to them. Okay, let me recap what we talked about in the last lecture about cache blocks and spatial locality. So before that, we started off with this very simple cache organization where we said we would store the full address along with the data. So let me go through an example here. So we said we'll store the full address 0, 1, 2, 3, 4, 5, 6, 7. I'm just assuming in this case that I have the addresses from 0 to 7, but of course the addresses that would be cached would depend on what addresses that a program would access. Now we said the problem with this approach is we are spending too many bits in cache for storing the tags. So we wanted to reduce the number of tags and the tag size. So the way that we accomplish that is by saying, well, for every cache line, instead of just storing 1 byte worth of data, let me store maybe 2 bytes worth of data. So what that means is I don't have to store these extra tags anymore. Not only that, it turned out that if you look at these addresses now, and if I look at these addresses, you'll notice a pattern. These addresses that are stored as part of tags are always divisible by 2, and that's not a coincidence. It's because of the fact that we chose the block size to be 2 bytes, and therefore in a byte addressable architecture, the addresses that you would need to store for the tag would also be divisible by 2. So if they are divisible by 2 all the time, you will notice that the last bit is always 0. Okay, now that means we don't really have to store that. In fact, the last bit is really used for identifying whether I should be accessing the first byte or the second byte in the block. And so that's why we call this bit as a block offset. Now the number of bits that you need for the block offset would depend on the block size. So turns out that the block offset size would be log to the base 2 of the block size. So in this example, I have the block size of 2, and that's why my block offset size is just 1 bit. So I don't have to store my block offset as part of my tag. I just need to store the tag, right? That is enough to identify whether I have that address or not. So instead of these tags, I would be storing 0, 1, 2, and 3, right? They're not the actual addresses, they are just the tag part of an address. So now what that means is now an address has 2 parts to it. It has a part called tag and then a part called block offset. And like we said before, for this example, the block offset size is 1 bit and the tag size is 3 bits. So what you see on the right hand side, this picture is I have taken the addresses 1 to 15 and partitioned them into tag and block offset, right? And you will notice that the first 2 bytes correspond to the tag 0. So when I move if I access any one of these 2 addresses, I would move this entire block into the cache. Okay. Now the second concept we talked about in the previous lecture is this idea of spatial locality. The spatial locality is an idea that if I access an address X, I'm more likely to access addresses that are adjacent to it. So it could be address next to it or the address previous to this address. So the address x plus 1 and x minus 1 are more likely to be accessed than address x plus 2 and x minus 2, and so on, right? Now, a cache block naturally exploits spatial locality. So larger the cache block size, the higher the capability to exploit spatial locality. Now you may ask, okay, why can't I define a block size that is really huge? Then I would be very good at exploiting spatial locality. It is true only if your program exhibits that much of spatial locality, right? So if I define a block size of, let's say, 16 bytes, then I would bring this whole memory into my cache, and hopefully your cache is big enough to hold all that data. But if I'm going to access only, let's say, 4 out of those 16 bytes, then the rest of the data would get brought into the cache and never get used up before it gets evicted. So you end up wasting a lot of memory bandwidth in bringing data in that you never use. So empirically, you have to find out what is the right block size that makes sense for most of the programs, and then choose that to be your answer. All right, so now we have a completely different problem. So far we've been talking about how do I reduce the number of tags and how do I reduce the tag size. We have one more problem in comparing the given tag from the address to the tag that is stored in the cache. So in this example, I have 4 cache blocks. So if I give you an address, then I need to compare the tag in the given address to all 4 of those tags. And if you go back to lecture 17, we talked about a structure called CAM, Content Addressable Memory, that is capable of performing these parallel comparisons. While we have the capability to do it, there is a limitation to how much we can scale the structure. So when you increase the size of the cache to, let's say, a few kilobytes, then the number of tags would grow proportionally to the number of cache lines. And so at some point, it would take enormous amount of time to perform all these comparisons, even though they are all done in parallel, because the cache area would be huge, and the time it takes to wire and send the signals to all these parts of the cache would be time consuming. And it's also area efficient because you need these comparators implicitly built in. So either ways, it's very inefficient to do so many comparisons to find out where my data is. And keep in mind that there is going to be exactly one place where you're going to find data, right? You're not going to store the same address in 2 different places. All right, so now how do we reduce the number of comparisons that we need to make in order to determine if it is a cache hit or a miss? So the main idea, and this sort of takes us to the idea of a direct mapped cache, is we are going to try and restrict the number of cache lines that a given cache block can be stored in. So if you think about our basic baseline design, a given cache block, let's say the first one we have with the tag 0, it can pretty much go into anywhere in these cache lines, right? So depending on which block gets evicted, I would use that cache line to store this block, right? So this freedom comes at the cost that I just explained earlier, which is that you need to do a lot of comparisons. So the solution is to restrict the number of cache lines that a given cache block can be placed in. How do I do that? Well, maybe I can think about this cache like an index structure, similar to how you think about an array and how you use an index to access an array. You can maybe think about this cache as an array with 4 elements. And you will want to use index to determine which element in the array you want to use. So how do I create this index? Well, obviously it has to come from the address, because the address is what you're trying to access. And we have already used up 1 bit for the block offset for this example. Now maybe I can use the next few bits as the array index, right? So in this case I have 4 cache lines, 1, 2, 3, and 4, right? So maybe I need 2 bits then. So if I have 2 bits from my address, I can then use that as an index to determine which of these 4 cache lines I should use to store a given cache block. Right. So as an example, let's say for the first cache block, the array index would be 0. So I would be forced to store it in the first cache line. For the next cache block, the index is 1. So I would be stored to store in this cache block, cache line, second cache line. Similarly, the third one will be stored here, the next one will be stored here. And now if you look at my tag 4, the last 2 bits, these 2 bits that I have been using as an index, it is 0, which means that it will map to the same cache line as the block address 0. So block address 5 will map here, block address 6 and 7. So when I talk about block address, I'm talking about the tag so far, right? The tag that we had in our original design. I'm talking about that as a block address because I don't really need the block offset, which basically tells me which byte in the block. So the block address is effectively everything in your address except the block offset. So the block offset mapping would look something like what I'm showing here if I choose 2 bits to index into this array of cache lines. And so I can continue this even So 7 would basically correspond to the last address that we have here. So you will notice that there is exactly 1 place for every cache block to be stored. And that's good because now when I have an address, let's say I want to figure out do I have the cache block with the tag 100, which is value 6, I can go and check, well, is the tag matching the value 6, and if so, then I can check if it's a cache hit or a miss. I don't have to check all the tags. I just need to compare it to the tag that corresponds to the cache line that I can store this particular block in, right? So the upside of using index is that it reduces the number of tag comparisons to exactly 1, because the index tells me which cache line I can store that block into, and I would retrieve the tag stored in that cache line, and that's the only tag I need to check. Now, even though you may be wondering, do I really need to do a comparison? Because I know exactly which cache line I'm going to store in, so just go and access the data. Well, you don't know which of the different cache blocks that can map into that cache line is stored at any point. So for example, in this first cache line, I could either store the block address 0, right? Or I could store the block address 4. How do I know which one I have stored at any point? Well, I have to check the tag to figure that out, okay? All right, so the last point I want to make here is the tag now doesn't have to be everything but the offset. I don't have to explicitly store the index part as part of the tag, because just like what we did before where we said we don't need to store the block offset because it's always going to be the same, the address the tag that is mapping into a given cache line, you would notice that it always has the same 2 bits for the least significant bits, right? So 4 is going to be 100, this is going to be 00, so you'll notice that the last 2 bits are always zeros. Well, that's not a coincidence, right? Because we intentionally used the last 2 bits in the tag as an index. So it's always going to be that. So the index does not have to be stored explicitly as part of the tag. So now my tag is going to be the entire address, but it doesn't have the index part minus index, because when I say minus index, I mean the part that contains the index. Maybe a better representation would be, so if I have an address, previously I had broken that into tag and block offset, but now I have used a few bits here as index, which we just argued you don't need to store as part of the tag. So that part goes away. So this is my full address, and in that address I have 3 components. One is a block offset, which is defined by the size of the cache block, and then I have the cache index, which is defined by the number of cache lines you have. So the number of bits I need, the index size, is going to be log to the base 2 of the number of cache blocks, right? So in this example that we had 4 cache blocks, so that's log to the base 2 of 4, and the answer is 2 bits. And that's why we used 2 bits for the index. And before we had talked about how it's going to be 1 bit for the block offset, because there are 2 bytes per block. And then the remaining is going to be tag, and given that this is a 4-bit address space, which is what we have been talking about, so the tag would be just 1 bit. Let me more precisely define the terms we talked about, and I will also go through a simulation of a cache architecture to illustrate the idea of a direct mapped cache. So the cache that we have been talking about all along, there is a technical name for it. It's called fully associative cache. And the reason why it's fully associative is because a given cache block can be stored in any one of the cache lines in the cache. So in this example, a cache block can reside in any 4 of the cache lines shown in the picture. And like we talked about, this has a tremendous cost in terms of tag comparisons, both in terms of the area cost of implementing a CAM for these tag comparisons, and also the time it's going to take for you to perform that CAM lookup for every address. And both of them scale as you increase the number of cache lines. Now, the alternative that we talked about is called the direct mapped cache. And the idea here is that instead of giving the freedom to store a cache block in any cache line, we are going to say there is only one cache line where a cache block can be stored in. And that cache line is going to be determined based on the index, which is derived from the address. So we are treating the cache, which consists of a set of cache lines, is effectively an array, and then we are going to index into that array to select the cache line. And the index that we are going to use comes from the address. So we had used previously 1 bit for the block offset, so now we have 2 bits for choosing one of the 4 cache lines. And whatever that is left over from the address is going to be your tag. Now, we also talked about the fact that many cache blocks can map to the same cache line, and that is highlighted by the colors that are shown. So any cache block with the address index 0 will map to the first cache line. So these two cache blocks will map to the first cache line. This one and the blue ones will map to the same cache line. So when I say they map to that cache line, what I mean is when the program accesses one of these cache blocks, they will be stored in the corresponding cache line, and they're all color coded to help us understand where they can get stored. And the one point that you want to take away from this is at any given time, only one of the cache blocks that can map to a cache line can be stored, obviously, right? Because the cache line has space only for one block. So I could either store this blue block or this blue block. I cannot simultaneously store both of them at the same time in my cache because of the restriction that I have imposed on myself, where I say these two blue cache blocks must be stored in this blue cache line, and so at any point only one of them can be stored. So that is the trade-off that we are making here, because it's quite possible that I'm not really utilizing the other cache lines at all, right? And the only two blocks that a program is interested in are these two blue blocks. So in that case, I would be not utilizing all the available space in the cache. And these two blue blocks are going to compete for this one cache line. So they may kick each other out as a program accesses them. And we're going to refer to the misses, cache misses incurred because of such conflicts between each other as a special type of cache miss called conflict cache misses. So we're going to come back to this idea of a conflict cache miss later on and define them more precisely, but I want you to get a sense of what that is. So here is another representation of what a direct map cache looks like. So an address again is composed of the block offset, the line index, which is what we talked about to select the cache line in a cache, and the remaining is a tag. So you would use this as a index into the tag array. So think of this exactly like how you would think about accessing an array in your C program, where you will say something like A of I, right? So where you access the ith element in the array A. Similarly here, the line index tells you access the ith cache line. When I say access, what I mean is the cache block corresponding to this address would be stored in the cache line corresponding to this line index, and there's a data array corresponding to that. And so whenever I want to access the cache, I'm going to take this line index, get the access to the tag, and then compare if this tag matches with this tag or not. And so if the tags match, then I know that it's a cache hit, and then I can go and retrieve the data that is stored in my data array, and then provide the block offset to select one of the bytes in the cache block, because that's what I'm ultimately interested in for a given address. So one of the properties of the direct map cache is that for a given index there is exactly one cache line where it can be stored. So we also talked about conflict misses. So here is a pathological example where we are assuming that addresses A and B have the same index bits, so they map to the same cache line. As a result, only one of them can be stored in cache. It doesn't matter how big your cache is, because they both map to the same cache line, only one of them can be stored at any time. And so if you have a program that is going to access A and then B, A and then B, you can see that when I access B, A has to be kicked out. So when I access A again, that would be a miss. So First time I access A, that's a miss. First time I access B, that's a miss. But the second time I access A, it's also a miss because B kicked me out, right? And then second time I access B, that would also be a miss because A would have evicted B. So each one of these accesses ends up being misses. So irrespective of your cache size, for this pathological reference pattern, you would have 0 hit rate. This is a pathological pattern. In reality, direct mapped caches perform reasonably well. But there is this trade-off that we are making where we are saying we are going to forego the freedom of storing a cache block anywhere in the cache, but in return we have to incur higher cache misrate. So let me walk through an example, animate and simulate the cache to get a sense of how this direct mapped cache would work. So in this example, I have only 2 cache lines. So as a result, the index bit is just 1 bit. I still have my 4-bit address space with 16 bytes of 16 bytes of data in memory. And so my address has 4 bits. We have used 1 bit for the block offset. So you see that there are 2 bytes in the block. And the remaining is going to be a tag, and so in this case there are going to be 2 byte tags. So anytime you're asked to simulate a cache like this, you would be given a reference sequence, and so for every address you have to split that address into these 3 components for you to be able to understand where that cache block would be stored. So the next question is, do I need to really worry about the replacement policy for direct mapped caches? Well, it turns out the answer is no, because recollect that there is exactly 1 cache line where a cache block can be stored, and so when you bring in a new cache block, you know exactly which one to evict, whatever cache block that is going to be stored in the cache line that you are indexing into. So we don't really need a replacement policy in this case. So let's take an address 1 and then split that into different fields. So I have done this on the right hand side, so we don't have to keep doing this again and again. So the index is 0, the tag is also 0. So I would update my cache line to reflect that. I have brought in the data, I update my register because it's a load instruction, and it's going to be a miss. I load my second address 5. Again, it is the tag is 1, index is again 0, which means that it would conflict with the tag that is currently stored in the cache. So 1 does not match with 0, which means it's a cache miss. So the current cache block would be evicted and replaced with the new cache block with the tag ID 1. So this is also a miss. So you notice that the tag changed. So now let's go to the next instruction, store, which is accessing address 2. So we have the split here. So you will see that the index is 1. Fortunately, we don't have any valid cache block stored. How do I know that? I can check my valid bit. So this is the first time I'm going to be using this cache line, and I'm assuming that it's going to be a write allocate policy. So I would bring in the data, I would allocate a cache line and bring in the data and set the dirty bit because I just modified the data based on the R2 value. And then I have another store instruction to address 7. The index is 1, tag is 1, so index 1, tag 1. So the tag does not match with what I have stored, so it's going to be a miss. I'm going to replace it. But before I do that, I have to evict the current cache block, and I don't have to worry about doing anything else. But in this case, I have a dirty bit set, which means that I need to write back the data into memory, and then I bring in my cache block corresponding to the address 7, and I would write it with the data that is stored in R1, which is 29, which I have stored here. So finally I have address 4, which I'm trying to load, and the tag for that is 1, index is 0. So I would compare this tag with this tag, and it turns out to be a match, which means it's a cache hit. And it's a cache hit because it's due to spatial locality. So remember that this is the first time I'm accessing 4, but in the past I had accessed the block containing 4 and 5, and therefore both were brought into my cache. So now I'm able to turn 4 into a cache hit because of that. So in the end we have 4 misses and 1 hit due to spatial locality towards the end. We will work out a few problems. So we are asked to simulate a cache for a different address sequence. The given cache has the same geometry as the one that we discussed before. So it is a direct mapped cache with the write allocate and write back policy. So write allocate means when you have a store to a cache block, and if it's a cache miss, you would allocate a cache line for it. Write back policy means when you have a store, you would write to your local cache, and only when the block is evicted, you would write back to memory. So now this is a 4-bit ISA, same as the problem we had before. And so what I have done on the right hand side is divided the given addresses into tag, index, and block offset. Okay, I have gone ahead and simulated for addresses 3 and 12. And so if you look at address 3 and address 12, you will notice that the index is 1 for this address, and the tag is 0, which is what we did. And so we set the valid bit to 1 because we brought in valid data. The dirty bit is 0 because we have not changed it yet. And then if you look at the address 12, the tag is 3 and the index is 0. So tag is 3 and we have stored it in the 0th cache line. Again, the valid bit is set to 1. So now I'm going to execute a store to the address 15. So the address 15 has a tag 3 and index 1. So this cache line is the one that is going to get modified. And the tag 3 does not match with the 0. So this line is going to get evicted. And because it's a write allocate policy, I'm going to replace it with the block with the tag 3. The value that I'm going to write is going to be defined by the register R2. So R2 is going to write 19 to the second byte in the block, which is what happened here. So I fetched this block and I overwrote 225 with 19. And of course the memory is not going to get updated because it's a write back cache. So therefore I just need to set the dirty bit so that when this block does get evicted, I would make sure to write back the data into memory. So the next address for us is 4, tag is 0, index is 0. Sorry, tag is 1, index is 0. So this cache line will be checked for tag 1. It's going to be a cache miss because the tag doesn't match. And so I would have to do the same exercise that I did for the address 15, which is to bring the data in and write the value 123 to the first byte, 71. Right. So I have bring this byte into the cache and then overwrite 71 with this write and set the dirty bit to 1. Okay, so finally I have the load instruction to 13. 13 has a tag 3 and index 0, and so If you noticed, I had a dirty bit set. The tag was 1, so the address tag 3 doesn't match with 1, so this would be evicted. So when it's evicted, I have to write back the data. So I have to write back the entire cache block because I don't know which byte in the cache block was modified. I just know that the cache block was modified. So now I have to write back both bytes. And so because I had not modified this would be a redundant write, but we can't really do anything about it. But 71 would be modified with 123. So if you see, 71 was modified with 123. And the cache block was modified with this new tag for the address 13. Okay. So let's look at another cache problem. So in this problem, we are given certain information about the architecture and the cache design. So I have a 32-bit address, and the number of the size of the cache is 32 kilobytes. Each block is of size 128 byte. Now this is more realistic, and it's a write back cache. So now we are asked to figure out the overheads of this cache, and that would require that I figure out the number of tag bits. So to figure out the tag bits, I need to figure out a few things before. I need to know the number of cache lines. So that is going to be the size of the cache divided by the block size. It's often easier to do this math if you convert everything to 2 to the power of something. So 32 is 2 to the power of 5. Kilobyte is 2 to the power of 10 divided by 128 is 2 to the power of 7. So 15 minus 7, that is 2 to the power of 8. So the number of cache lines would be 2 to the power of 8, which means now the index size is going to be log of the number of lines. You just figured out the number of lines is 2 to the power 8, which means it's going to be 8 bits. So now that we have the index size, let's also compute the block offset size. So the block size is 128 bytes. So the block offset size is going to be log of 128, which is going to be 7 bits. So if I have a 32-bit address, I have 7 bits of block offset, 8 bits of line index, the index that you use to select the cache line in a direct mapped cache, and then the remaining, which is 32 minus 8 minus 7, which would be 32 minus 15, that will be 17 bits. So an address is composed of these 3 parts. This would be the tag, this is your index, and this is my block offset. So the tag size is 17 bits. So now for the overhead of the cache would include several components. So one of them is tag size, but I also need to have a valid bit, then a dirty bit. So it's going to be 19 bits, and I have 2 to the power of 8 cache lines. So I have the total number of cache lines. So for each cache line I have 19 bits of overhead, so the total number of bits I need for the metadata is 19 bits times 256. Now if I divide that by the cache size, which is the size usually is represented in terms of the useful data, so I'm dividing the overhead by useful data to compute my cache area overhead. So far we've been talking about caching data, but keep in mind that when you execute a program, you need to bring in both instructions of that program as well as its data. So where do you store instructions? Like data, you store instructions in memory as well, and those instructions are also stored as part of data in the program's address space. So when you access instructions, so when you execute any instruction, you need to access memory to get its instruction machine code. And so for every instruction, you have to access the memory system. Obviously, accessing main memory for every instruction would be expensive. So just like data, we would like to cache instruction as well. And so for all cache design problems, you can pretty much assume that instructions are treated in the same way that data is treated, in terms of how you store them in the cache, what kind of a replacement policy makes sense, and the direct mapped cache that we talked about may also make sense. Now, the only time when it actually makes a difference or a distinction is for the L1 processor cache. So when we designed the memory hierarchy, we said we have a cache at the top of the hierarchy, and then we have the main memory, and then we have the disk. So in the previous lecture we said, well, in reality, cache is not just one structure, but it is actually composed of several levels. So you have level 1, level 2, level 3. Level 1 is the smallest one, level 2 is slightly bigger, level 3 is even bigger. And the reason why we use so many levels is to bridge the space and latency gap that exists between a small L1 cache, which is of size 32 kilobytes or so, with main memory, which is several gigabytes, and it takes hundreds of cycles to access. L1, on the other hand, just takes one cycle to access. Now, L2 and L3 stores instructions in the same way that you would store data. So there's not much difference. But for L1, in some processors, they choose to have two L1s. One for the data cache, like we have been talking about, and one for the instruction cache. So now, what are the advantages of having two L1s, one for instruction cache and one for data cache? Well, L1 is a level 1 cache, and it happens to be very sensitive to latency. So we want to be able to access these L1 caches really fast at the clock cycle of the processor. So one cycle, which is 1 nanoseconds. So we can't really afford these caches to be too big. So we can use either one cache, let's say a 32 kilobyte cache, and store both instruction and data in it. So in that case, instruction and data are going to be competing for space with each other. Alternatively, we could say, well, let's have two caches, two L1 caches. One stores data cache and one stores instructions. Now, the advantage of this is when I have a instruction fetch, I know exactly which of these two caches to access, because instructions are going to be stored in the instruction cache, so you just need to access instruction cache. So even though in aggregate I have two caches and the total size is twice that of what I would have otherwise had, the two structures are isolated, so the time it takes for me to access an instruction cache is only proportional to the size of the instruction cache. So the latency doesn't increase. Of course, the area doubles, but the latency of accessing instruction cache does not increase, which is super critical for this level 1 cache. So the main advantage of having these two caches is that the instruction fetch would access instruction cache at a very fast time, and then a load or a store instruction in the memory stage of the pipeline would access the data cache, and again they can operate very fast. So if you look at the pipeline diagram now we can replace the structures with our instruction cache and data cache, right? So now these are a little bit more realistic representation of what an actual processor looks like. And instruction cache and data cache, which are level 1 caches, they operate at the speed of the processor clock cycle. So if you assume that the processor clock cycle is 1 gigahertz, they can operate at 1 nanoseconds, and so you would not observe any extra stall than what we had already assumed in our pipeline design. However, we can have cache misses, both in instruction cache and data cache. And when you encounter those cache misses, you're obviously going to be stalled for the time it's going to take to access the next level of the memory hierarchy. So if it is the next level is level 2 cache, it may take maybe 10 cycles to get there. But if the next level is main memory, it's going to take 100 cycles to get there. So it's going to take a long time for these cache misses to be serviced. Modern processors have ways and mechanisms to somehow do useful work when you are waiting for this data to come back. So there are ideas like out-of-order processors and prefetching, etc., that are being employed to solve that problem. We won't go into the details of those ideas, but if you take 470, you can dig a bit more deeper into those challenges and ideas. All right, to summarize, we talked about direct mapped caches today. The main idea to take away is that if I have the freedom to store a cache block in any cache line, then I need to do a lot of tag comparisons, as many tag comparisons as there are number of cache lines. So in this example, I have 4. So the main idea was I wanted to restrict the number of places that a cache line can be stored in. So we went and said there is going to be exactly 1 cache line where you can store a cache block. And so the way you would figure out which cache line it's going to be is by using a few lower order bits in your address, and the remaining bits in that address would be the tag. So in the next lecture, we're going to be talking about what's called as a set associative cache. Now I'll briefly introduce set associative caches today, and then I will go into a bit more depth in the next lecture. So the downside of the direct mapped cache is something that we identified when we talked about conflict misses. So the problem is it is too restrictive. So when we talked about fully associative cache, it is too permissive in terms of where you can store the data. And direct mapped cache goes to the other extreme and says, well, there is exactly 1 cache line where you can store the data. And that can lead to performance loss, because if the program happens to access the cache blocks that are mapped to the same cache line, then only one of them can be stored. So you have this thrashing effect where one block would kick the other block repeatedly, and then you don't really use the cache productively to cache anything, right? So we had talked about this pathological ABA pattern where A and B are mapping to the same cache block in a direct mapped cache, and they keep kicking each other out, and then you end up with all misses. So we want to give a little bit more freedom than just saying, okay, 1 cache line is where you can go to. How about 2 cache lines? And how do we architect that? Well, that takes us to set associative caches. So now I have 2 cache lines that are colored in the same way. So I'm going to call that as a set. So I have the cache line 1, cache line 2. Both are grouped together in the form of a set. And I have another set with exactly the same geometry. So before I was using index to select one of the different cache lines. Now I would use this index to select one of the cache sets, where each set is going to be a set of cache lines. Now, why is this better? Because now if a cache block maps into a set, right? Because the set index is only going to select the set, but it doesn't select which cache line within that set. So that gives us a more freedom, because now I can choose to store my cache block in any one of the cache lines within that set. I'm going to call the cache lines within the set as ways. That's just a technical term for referring to the different cache lines within a set. So I can choose whichever way I want to store in. How do I select which one? Well, we're going to bring back our ideas from temporal locality, where for a fully associative cache, we use this heuristic LRU, least recently used policy. Now, instead of applying the LRU policy for across all the cache lines like we did in the fully associative cache, now we are going to apply it only within a set, between the cache lines within that set. So we have these cache blocks that map to this set. So I'm just mapping to the set, not necessarily the way. So I have 4 cache blocks that map into this set, and so I can now choose one of the 2 cache lines that is available for storing it, and when both of them are full, I would pick the cache line which is least recently used among those 2.